So I'm planning to discuss with you about our thin film primerless consolidated layering for OEM. So what is different about this process? It's both primerless and thin film. While both primerless and thin film exist separately currently, we've combined these. So this takes the standard, this takes the standard application layering where primer is used typically at 20 to 40 microns depending on the technology, base coat of 13 or more microns and clear coat of 30 or more microns. So a total top coat film build of 63 to 83 microns. And shrinks that down, turning the primer into a base coat with some primer functionality of 6 to 10 microns for most colors. A second base coat also of 6 to 10 microns. And the clear coat is reduced by about 5 microns for 25 microns total. So this gives a total top coat film build of 37 to 45 microns for most colors. There is some variation for colors that traditionally have poor hiding, such as whites, where film builds are higher. So the additional benefit there comes in from the compact line design for this coating. So again, for standard conventional 3-coat 2-bake and traditional 3-wet processes, we still have the full bake or high temperature flash off oven between primer and base coat. Then high temperature flash off after base coat, clear coat, and then full bake after clear coat. With this process, we are able to eliminate that first oven after primer to give us the compact process of base 1, then base 2, high temperature flash off, clear coat with full bake. So overall, this allows for plant footprint and capital expenditure being reduced by up to 30%, depending on whether this is a new line being built or adaptation of an existing line. So why do we use primers? Why is it a big deal that we got rid of them? Primarily, they are used for light protection, so they help block visible and UV light from degrading the E-coat layer, which helps protect the steel. This is achieved through a combination of film build and high hiding power. As you can see in this graphic, most coatings, again, being derived of the primer, base coat, and clear coat layer, the clear coat provides protection against the UVs with UV additives and hals. The base coats then also block some light and UV, but it's very dependent on the pigment selection. So a lot of reds, whites won't protect as well, whereas then the primer helps protect against all the rest of any light penetration down to protect the E-coat entirely. Primers also help improve appearance. They cover up any defects in the E-coat layer and anything that needed to be repaired before top coat is applied. Additionally, primers help with chipping resistance. They balance soft and hard properties to disperse energy. So in general, they need to be soft enough to prevent impact damage, but hard enough to prevent easy scratching. So in this infographic, we have the impact coming down and hitting your coated surface. If your film is too hard, then that energy is dispersed in the direction of energy impact, which then allows for deep defects to occur all the way down to the E-coat or steel layer. Whereas if your film is soft, ideally optimized, that energy is then dispersed along the surface, so it just creates a small scuff, and your E-coat steel surface stays well protected. So what are some of the benefits of eliminating the E-coat? Primer. The downsides of primers, typically they require high film build. This creates risks, particularly for popping, sag. They require HFO or full bake before base coat, which is a high energy use. They also are difficult and costly to adapt for unique color positions, at least in my experience. Most lines try to limit the number of primer systems that they have, which then means that any colors you adapt to go over those primers either need to have a unique primer developed for them or have to be adaptable to the primers that exist. With this system, there's still a need for multiple base one systems, but it's easy to adjust those base ones for the color positions that are needed. Additionally, conventional primers are often solvent-based, which is high VOC. This system is water-based for both base coat layers, which helps reduce VOCs. So how does this technology of thin film primerless help address these needs? So for chipping, we use magnesium silicate body pigment, or talc, which is commonly used in most coatings. It is optimized for this technology to provide soft barrier to absorb impacts, and it's incorporated into both the basecoat 1 and basecoat 2 layers. So just as an example, if you have a system without any talc, I'm sure all of us who design paint coatings know the risks, but it will allow impacts to occur that causes damage all the way down through the coating layers. With the talc level optimized, it creates a good coating that prevents delamination below the base coat. So while there may still be coating loss, the coating loss will typically be within the top coat layer itself, so there's still adhesion to the substrate, which protects the underlying surfaces. If there's too much talc in your coating, then it causes delamination as well, as it breaks and interrupts the resin too much. Additionally, these coatings are designed with a higher level of polyurethane dispersion. Again, this is pretty common in most existing coatings, but it has been optimized for this, and the type and amount are used as a replacement for more brittle resins that are typically used in a base coat, such as acrylics. So just as an example, this is a very general version of a polyurethane made up of rigid sections and flexible sections, which then allows the coating to bend and return to its proper surface when impacts occur, so it can flexibilize. Additionally, these coatings are designed to help with the light blocking by ensuring that they have high pigment content, and the resins are balanced to ensure that that pigment content is able to be maintained without any downsides. Just as an example of some standard layering, for most standard colors, so not your premium colors, not whites, they use a film build of 6 to 8 microns for each base coat layer, with white and pore hiding colors typically being higher than that. For example, one of the whites that we have developed in this technology uses a base coat 1 film build of about 32 microns. So that kind of doesn't help with the thin film portion, but because of the consolidated application process, there's still a lot of cost benefit to that. But all of them are designed to optimize the light protection. A key benefit of this as well is that due to the dual base coat layering, unique and premium colors can be tailored by adjusting the base 1 and base 2s. Just in this little example here, we have one common base 1 in this kind of magenta color, but then we can use 2 different base coat 2s to achieve 2 different color positions. This is just an example, but then for e-coat considerations, so one of the things I've mentioned multiple times during this presentation is that most current colors or coatings are designed to help protect the e-coat. So for this, we recommend the use of specific types So most standard e-coats are sensitive to delamination with marginal hiding top coat systems. If the e-coat is overbaked or turns green or brown from that overbake process, it does make them more sensitive. In this example here, I just have what a typical not overbaked e-coat should look like and what a slightly overbaked e-coat should look like. Standard e-coats can also be exposed to and are sensitive to the visible portion of the light spectrum past where most UVAs would protect. We recommend e-coat that's been designed for compact top coat. The one that we provide is formulated to reduce oven oxidation. It's more forgiving at a low bake window, minimizes overbake for e-coat layering, and there's space within its current design to optimize for further durability if needed. All of these combined help reduce the risk of chemical breakdown, leading to delamination when exposed to UV or high energy visible light. So while our top coat is designed to prevent light penetration to the e-coat layer, the additional protection from the e-coat helps prevent the substrate. Then just information on the base coats themselves. So base coat 1 is designed with high pigment concentration, again for that light protection. It has a high loading of polyurethane dispersion. It can be made with and without effect pigments, depending on what the desired finished color position is intended to be. It also is designed to be more hydrophobic, so even though it is a waterborne coating, it's designed to be hydrophobic primarily to ensure good compatibility with base 2 without them blending into each other. Then base 2 is designed for high pigment concentration. It has also a higher PUD level than a standard coating, but lower than the base 1. Typically contains effect pigments and UV additives. Then both of them are designed with the NV and viscosity or rheology optimized to allow for good appearance, particularly in areas where there's overdusting, so along interiors, crossover sections, and as well as to prevent sag and pop at high film build areas. And then the clear coat that we have for this system is a 2K polyurethane clear. Since this is a thin film build technology, 2K is generally the best way to go forward because it's going to offer better durability than a 1K clear coat. This improves performance with isocyanate migration. It's also higher durability than a 1K, as I said. In the technology, sorry, I'll get the button right eventually, I promise. In the clear coat we have, we use a similar isocyanate to the one pictured here. This is just an example, combined with an acrylic resin that is designed for a shorter branch chain. This creates a tighter cross-link structure, which is more durable than a longer branch, which is typically used more for polishability performance. So implementation considerations. So film consistency, which we know we get at the customers that currently purchase the technology. This is controlled through paint properties and application settings. Again, optimizing that overdust and overlap area on the vehicle. It's also very important that you use robot application. Given that this is thin film, using hand spray makes it very difficult to ensure that you're getting consistent film build across the surface. We're also able to ensure, or you need to make sure that you have good flow rates adjusted for the film build targets, with most of the colors that we currently make using a flow rate of between 90 and 140 cc's per minute. Then for color stability, this is again controlled through applications, teaching and settings. Many individual colors require semi-unique settings, particularly for bell speed and shaping error. Additionally, this technology is successfully used for bumpers using adhesion promoter. It's compatible with water-borne adhesion promoters that are designed for polypropylene-based bumpers, and 2K clear coats designed for use with water-borne basecoats. Currently, it's typically used with a low bake system of about 90 degrees total for the clear coat at current customers using AdPro and clear coat designed by us. So how do we design these colors? We typically start with receiving the color target, whether this is an existing CSP target or a new design color. We then proceed to assess if the color could share a base coat 1 with an existing color. And then if yes, develop a base coat 2 color position, and then confirm process window is feasible. If not, we'll go back to the developing of the base 2 color position until we reach a point where that feasibility is achieved. If there is no base 1 that can be combined with it, then we'll follow the same process, but we'll be designing both base 1 and base 2, ensuring process window is feasible for both of them. Once that is complete, then we'll proceed to film and paint performance testing and line trials. All throughout this process, we try to make sure that plant engineering is involved as much as possible, because while we as the supplier have a pretty good idea of what is feasible for the line, they have the best ideas of what can and can't be done. So it's important to keep them involved, especially if we're designing a premium color that may go outside of the standard window. All right, then just as a quick example of our current global track record, so currently we're able to successfully manufacture these materials in 4 countries, and we currently successfully run these materials in 5 countries globally. I blew through that pretty quickly, but if there's any questions, and thank you for your attention.
Don't go anywhere. You've got quite a few questions. Okay, the first one is, does the overall reduced film build provide any inherent benefits?
Primarily to cost and usage. So you won't be needing to use as much paint, and overall that reduces the energy for the plant because you're not baking off as much material as well.
Are there any concerns with talc usage going forward with increasing regulations due to carcinogenity?
Not currently.
Okay. How does the long-term weathering performance of the Primerless system compare to conventional coating systems?
Based on our lab testing, there is as good durability as conventional coatings, and then these coatings have been used in the field for more than 10 years with no concerns.
Okay. At what percentage of hiding is light transmittance tested or validated?
We test at the minimum target film build for each one, and typically layered together at various combinations. We target to have 1.5% lower, a maximum of 1.5% light penetration through the coating.
Okay, what is the minimum base coat 1 film thickness that can be used and still protect the E-coat?
It varies by color. Of the colors we currently have designed, the minimum is 5 microns.
Okay, next, we're still going. What is your light transmission specification?
It varies by customer. So if you have specific requests, I can discuss that with you separately.
How is this different than a 3-wet system from an energy savings perspective?
At least 3-wet systems that I'm familiar with, it allows for the elimination of that. Sorry, going back like all the way to the beginning. It allows for the elimination of the first bake. So at least from the presentations that I've seen today, it appears that there are other materials on the market that are more similar to this, but they are higher film build.
Has Nippon Paint commercially applied the thin film primerless layering process?
Yes, we have 10 plus years of commercial history.
How is the cost of color development compared to conventional?
It depends on the color position and what pigmentation is needed, but probably fairly similar for the development side. But again, it varies a lot depending on what color we're talking about.
Okay, just a couple more. How many base coat ones are needed to support a full color palette of base coat tubes?
If we're talking about a color palette of, say, 8 colors, probably 5.
Why is this technology limited to bumpers?
I don't know that it's limited to bumpers. That's just the extent that it's been tested. If there's interest in other plastics applications, we're happy to talk to you about it.
Okay, and the very last question from the app. Your target film build of 6 to 8 microns for base coat layers is on the order of thickness variation we would like to see over a vehicle surface. How do you manage film build and color uniformity?
We work with the customers or OEMs to ensure that they have application settings that can be met. So adjusting the bell speeds, flow rates, shaping air, anything along those lines.
Okay, any other questions from the audience? No?
All right.
Okay.
Thank you,
Thank you.
everybody.